workshops to give the math colloquium. And I thought that that was a good idea, so I arranged with Jesper Jacobsen to do that. However, this morning on the email, there's this email which says that, due to an abundance of caution, the university is closed today, all day. There will be no classes and no events. Fortunately, this is not classed as an event, so we are able to proceed. But that means the audience is substantially decreased. So outside of Dennis Sullivan, who's
Misha.
And Misha, the number of mathematicians here is drastically less than we had hoped for. So instead of having a small number of people huddled around the forecourt in the large auditorium, holding it here is a much more intimate setting. So the speaker today is Jesper Jacobsen. He comes from École Normale. He's a very helpful person in doing research because he speaks Danish and therefore he's able to communicate with Danish colleagues otherwise who will not return anybody else's emails. I've worked with him for several years. He has a wealth of information, and I persuaded him to give another version of the difference between integrability and non-integrability, and I hope you may explain what the poster is all about. Just
Thank you very much. Well, thanks for setting up this math colloquium, and thanks to the mathematicians, or some of them, for coming. So I believe there are two ways of doing a math colloquium. So one is to pretend as a physicist to do some math and try to prove some things. Usually that doesn't end very well. So the other strategy is to just be honest and say that we are physicists and we have some problems getting the math right. So that's what I'm going to do in this talk here. So there is going to be a lot of open questions. There are also going to be a few math results, but not so many. So enjoy. So here are my collaborators. So the main part of the work that I'm going to present is in collaboration with Michael Assis, Ivan Jensen, Jean-Marie Maillard, Barry McCoy. I will touch upon some old work that I did with a former thesis student of mine, Jean-François Richard, and also of some work I've been doing in collaboration with Jesus Salas and Alan Sokol. So the motivation for this work is to try to learn something about the analyticity properties of the two-dimensional Ising model when we apply a magnetic field. And that's obviously a very difficult problem. So that's why in the beginning of the talk I'm going to focus mainly on some special cases which are in the limit of an infinite magnetic field, taken in a limit with a certain ratio between parameters that makes it equivalent to lattice gases of hard squares or hard hexagons, depending on what lattice I do it on. And already in those limits we are going to see the differences between integrable and non-integrable systems and the various ways in which they interplay. So as I said, there is not going to be so much rigorous math in this talk. There's going to be a large proportion of observation or experimental math, and there will be many open questions that will be presented but not solved here. So I hope you are fine with that, and just to make sure, you can sign our liability waiver form that will circulate. So so what's the Ising model? Well, that I guess all of you know. So you take some regular grid, so a two-dimensional graph with vertices and edges, and you define spins, which are variables plus minus 1 on the vertices, and they interact along the edges. And in particular, we shall be concerned with the case where G is a piece of a square or a triangular grid with certain boundary conditions. And the boundary conditions are going to be quite important, as we shall see, because in particular in the cases where we have a non-integrable system, there is a there can be a very important dependence on boundary conditions, something that we might not be so used to. That being said, many of the talks that we have heard this week also stressed similar phenomena. So,
even for a large square.
Yes.
There's some.
Right. You will see. So that will form part of the questions that I will ask people to help solving. So the interaction energy of a configuration of those spins, those variables plus minus 1, is given by this epsilon here. So you see that if you want to lower the energy, then it's preferable, provided that k is a positive number, it's preferable for these spins to align. And then there is a magnetic field which can turn them preferentially in one direction or the other with a parameter h. So k is the coupling, h is the magnetic field, and curly E is the energy. And we're going to study this, of course, through the partition function. So everything is weighted by the Boltzmann factor, exponential minus beta E. And so one easy way to think of this in terms of some parameters that I shall use extensively, u and x, is that you can just think that all spins being up, that's some kind of reference state. And then whenever you turn one spin down, then you are going to get a weight of x. And in addition, if you have two nearest neighbors that originally were aligned, if you now disalign them, you are going to get a weight square root of u. That's a 1 unit of domain wall. But since on these lattices here, the domain walls always have even length, it's better sometimes to work in terms of this variable u, which is the weight for 2 units of domain wall. So there's a certain limit in which I can get lattice gases out of this problem here. So if G is the square grid, then if I fix x times u squared to be some fixed number and take x to 0 and u to infinity, then you see what will happen is that if I have spins which are plus all over the place and I have a single downturned spin, then on the square grid that comes with 4 units of domain wall. So that is to say the total weight is going to be z of that, so that's finite. Suppose now that I downturn 2 spins. If those 2 spins are nearest neighbors, then the domain wall surrounding them will be of length 6. And that will go to 0 in this limit. However, whenever those 2 downturned spins do not touch each other, I will get 4 units of domain wall around each of them. And so I will get a z squared here, and that will not disappear in the limit. So more generally, what will happen in this limit here on a square grid is that I can turn spins down, but not when they are nearest neighbors. So each downturned spin, that's like a little hard square that doesn't like at all to have nearest neighbors. And so that's what we call a hard lattice gas, or hard squares. So they have an infinite repulsion between nearest neighbors. And in the same way, on a triangular grid, if I fix x times u cubed, because then there are 6 units of domain wall around each spin that is downturned, then I will get hard hexagons. And it turns out that hard squares is a problem which is not integrable, and hard hexagons is a problem which is integrable.
Which one is which?
Hard hexagons is integrable. But we shall see more about that. So some of the main questions are, what are the analyticity properties of the partition function? So there are various integrable cases, as I just said. The hard hexagon limit that has been studied first by Baxter and later by Baxter and Pierce. Also, the Ising model itself, when there is no magnetic field, is integrable, and it is so on any G. And that was, of course, pioneered by Onsager and many people hundreds of people have worked on this.
Any planar G?
Yes, but G was supposed to be a grid, and my understanding of a grid is that it's the correct math word for saying a planar graph, but that's one point again where maybe it's dangerous to speak in front of mathematicians, but I intend grid to mean that this is a planar graph.
Give kind of a short, intuitive explanation for the integrability in hexagonal case and not in the other case.
No, that's a complicated story.
That's what we're trying to learn.
Right. Well, okay. So actually, exactly solvable means exactly solved, right? So people here, Baxter has actually been able to solve the hard hexagon model to the extent that the partition function can be analytically computed, and no such progress has been made for hard squares. That might lead you to think that it's not possible to do it.
You don't mean it's not possible to do it. It hasn't been done yet.
The transform matrix behaves differently for the two, and that and all the integrable systems that have that one property and this one doesn't have it.
So we have some toolboxes for solving models, which is basically that there should be a certain setup in which they solve the so-called Yang-Baxter equation, and that is something that hard hexagon can be shown to do. And if you do the similar setup for hard squares, you cannot do that. And there are many different techniques that you can try to apply, and you can see that the two models really qualitatively behave differently. So that cannot really preclude the possibility that sometime somebody will come with a completely different idea which will enable us to compute the partition function exactly for hard squares. But no such result is known. And the most probable thing that people would believe when they have tried doing such things is that it would not be possible. But of course, something seems impossible until some smart guy finds out how to do it. So that is what I mean. There's some more specific motivation, as we have heard during the conference here. The square lattice Ising model, the magnetic susceptibility as a natural boundary in the U variable that was shown by Nickel. For the hard square problem, there is something particular going on when z is equal to -1. It turns out, as shown by Fendley and collaborators in 2005, that all transform matrix eigenvalues are roots of unity. That's a very particular property which has something to do with a supersymmetry in that model. And as far as I can tell, it doesn't really mean that the model, even at that point, is integrable in the traditional sense. Also, there is an very interesting piece of work by Fonseca and Zamolodchikov from 2003, who have studied the analyticity structure of the universal scaling function in the Ising model from a conformal field theory perspective. And there is some kind of interesting interplay between point 1 and 3, because even though there's this natural boundary in the model on the lattice, that does not prevent the people here in point 3 to study properties of the universal scaling function by various kinds of analytic continuation. So we shall be interested in the so-called bulk free energy here, basically the log of the partition function that's defined initially for u and x positive and real, and for the setup of thermodynamics to hold in a traditional sense, this limit should be independent of the aspect ratio of my grid and of the boundary conditions. And in particular, I should like to study rectangles of size LV times LH. V means vertical and H means horizontal.
How's the shape of the rectangle come into the formulation? It didn't come in, did it?
So I'm going now to shortly. I'm going to study this partition function here for finite systems which get larger and larger, and I'm going to study them initially on rectangles with certain aspect ratios. And then I'm going to take this limit, but you see, if I just want to send LV and LH to infinity, I can do so with various aspect ratios. So maybe the most natural is to take aspect ratio 1, but as we shall soon see, there are some advantages also to considering sending first one dimension to infinity and then the second. So that means that you take the limit through infinite aspect ratio, and the results are slightly different, and there will be some more questions to math people at that point. So one very popular way since the early 1950s to study analyticity properties is to look at the points where the partition function is 0 for a finite system. So you see log doesn't like to have a 0 inside, so that means that the free energy is going to develop a singularity. And when this f here is initially defined for real and positive u and x, one can try to define it for more generic complex valued parameters or negative parameters by analytic continuation into the regions which are 0 free, and that include the positive real axis. However, as far as I know, there is no general theorem guaranteeing whether or not I can do any further analytic continuation beyond the 0 free regions. And some outstanding question is whether there will be kind of solid walls of singularities that build up because of partition function zeros, so that I cannot analytically continue into certain regions. And it's certainly true that, and we shall see that analytic continuation does not commute with the thermodynamic limit. So let me be a little bit more specific about these models. So hard hexagons were first studied by Baxter in 1980. He found two exact expressions for the free energy. These two expressions are unrelated by analytic continuation, and they have singularities at infinity and in two very particular points, ZC and ZD. So that's a little z, that's the, oh sorry, I should say z, I'm in the United States, sorry. Well, I like saying z. So so that's the fugacity of particles. So there is one positive value, 11 and something, and there is one slightly negative value, minus about a tenth. And at those two values, there are singularities.
Two different expressions got which way?
So there is, so you see this 11 and something that separates the region of large Z from the region of small z. So when Z is large, it means that I put in a lot of particles because the weight is high, so that's a high density phase. And on the other side, when Z is between 0 and 11, that's a low density phase. So he found one expression which gives the largest partition function in the high density region, and another one which gives the highest partition function in the low density region. And those two are just very different analytic expressions. And right at ZC, this system has been shown to be conformally invariant, and it's in the universality class of the three-state Potts model. And at ZD, it's in the universality class of a non-unitary conformal field theory, which is called the Li-Yang edge singularity. Hard squares is not exactly solvable, or has not been exactly solved in that sense. Many results have been obtained for it by, for example, series methods by Tony Goodman, who is here, Gur, Blöte, Jensen, And the critical point is known to, I'd say, more than engineering precision. I mean, people doing metrology, they, I guess, nowadays consider things to be exact when they are defined up to 12 significant digits, and that's certainly the case here. So ZC and ZD are known. ZC does not have the same critical properties from the point of view of conformal field theory, because the lattice symmetry is different. When I'm on a triangular lattice, there are 3 sublattices, so that's why it's the 3-state Potts universality class. On the square grid, there are 2 sublattices, so I get Ising behavior, actually. But interestingly, at ZD, these 2 models, they are supposed to have exactly the same critical properties. We should talk a little bit about boundary conditions also. So in each of the 2 lattice directions, I can consider either free or periodic boundary conditions. I'll call that F for free and C for the last letter of periodic or the first letter of cyclic. So in particular, if I take periodic in both directions, then I'm on a torus. If I take free in one and periodic in the other, well, depending on in which direction I take it, I will call it cylindrical or cyclic. And if it's free in both directions, I will call it free. Obviously, ZFC equals ZCF if I permute the horizontal and vertical dimensions. But in a moment, we are going to construct the partition function from a certain linear operator, which is called the transfer matrix. And that transfer matrix, it points out a preferred direction. It's kind of a time evolution operator. And it certainly matters to that whether it sees the free or the periodic boundary conditions as it goes along. And so from that point of view, even though these 2 guys here are equal, the transfer matrices that build up the lattice in one direction or the other will be different. So here are some very interesting figures that you can see on the poster. Actually, the poster is this, but let me first talk about this. So for toroidal boundary conditions, for a lattice which has aspect ratio 1, we have computed the exact partition function for a 26 by 26 system for hard squares and for 27 by 20 systems for hard hexagons. So those are the zeros? And those are the zeros. Those are the zeros in the complex plane of the Z parameter, so the weight per particle.
Numbers of lattice size here.
Okay, so I have to, in order not to make the problem even more complicated than it already is, I have to respect the sublattice structure of these 2 lattices. So the square lattice likes the size to be even, and the triangular lattice likes the size to be a multiple of 3.
So you're sure that the difference in the pictures doesn't come from even odd?
Yes. So I would have liked to do 30 for both. But it just turns out that 26 and 27, that's precisely the point to which you can take state-of-the-art numerical computations. Okay, so I say numerical computations, but I should stress that the partition functions for those systems, they are huge polynomials with integer coefficients, and those integer coefficients, even though they have 40 or 50 digits, they were computed exactly. Okay, so the computer is doing this, but it's completely exact. So you see already here that there's a remarkable difference between those 2 pictures. You see here, the zeros, they fall on a very restricted number of very regular curves. And here, at the first side, it looks like they are just all over the place, at least in some parts of this diagram here. Well, there's still a little portion here on the negative real axis, which looks similar. And if you look a little bit closer, it looks like they form some arcs here or some rays going out. And that's all very interesting. And I don't even need to turn it into a question. Everybody can make his own question out of this picture here. Now I'll show some other boundary conditions. Okay, so these are cylindrical boundary conditions. In these cases, we can go to even larger systems, size 40 or size 39. We'll try just to look at the right figure here. I will switch back and forth a couple of times. Well, you see that they are basically the same, right? There's not much that varies on the right picture. On the left picture, well, that looks much more dependent on boundary conditions. Yeah, free boundary conditions. Okay, so I told you that for hard hexagons that Baxter has two analytic expressions. So those two analytic expressions, they are given in terms of infinite product formula. And in the complex plane, of course, they take complex values. But you can try to put them equal in norm and try to solve for the places in the complex plane where they are equal. And that is this figure here. If I go back and forth, you can see that it matches quite closely. It matches this part here and this part here. But then here is something that looks a little bit, well, we call it the necklace, just to give it a nickname. And this curve, it goes through in the middle here and has some cusp here, and then it goes down here. So clearly, Baxter's work accounts very beautifully for the places where the zeros sit on this portion of the phase diagram, but something extra is going on here. So challenge number one, what did Baxter miss? There must be at the very least, to account for this data here, there must be a third analytical expression, or maybe even more than three, of which only two were found. For example, it would be rather beautiful if there was a third expression that was just dominant within this necklace here, so that I get this and this. But then there's also something going on in the middle here. That's also interesting.
So the infinite lattice, isn't it?
Yes, well, okay, but these features here do not go away when I take the lattices to be larger and larger. I'll show you here size 39. Obviously, I also have 36, 33, 30, and so on. And all this stuff here, it's very clear when you look at its size dependence that it converges to something, and that something is basically what you see here.
Expressions are infinite products.
Yes. For the infinite system. So, observation. So the zeros, they lie on a few well-defined curves for hard hexagons. They depend little on boundary conditions, except maybe inside this necklace region where you see a few sporadic zeros here. And that those guys here, they sort of move a little bit around with system size. When L goes to infinity, the zeros pinch the real axis at ZC. That's the point over here. And the right endpoint of the straight segment tends to ZD. There is no segment here, but the segment is here. And here is ZD. Right, so in the zeros here, in the zeros for finite systems, they are going to accumulate a lot on this segment here on the real negative axis, and that segment that ends at ZD in the limit of a large system. It's not visible here.
But that's an ordered phase, isn't it? So then you expect
Put the outsides they would.
No, the outside.
Outside.
Large set is right. So Baxter's expressions, and let me call them F plus minus, plus meaning high density and minus meaning low density, they both have singularities at ZC and ZD and only there, and both, except from infinity, and both can be analytically continued to the whole complex plane cut along portions of the real axis, namely the interval between ZD and ZC for F minus, the complement of that for F minus, oh my God, and along ZC, sorry for the typo, to ZD for F plus. So, some open questions. Baxter's expression, they account for this main bubble, as we have seen, but not for the necklace region and not for the segment along the negative real axis. And the structure inside this necklace depends on L. Yet, when you look at sizes up to 39 times 39, the density of 0 seems to tend to something finite as L goes to infinity. That remains to be explained. For hard squares, the zeros lie on many curves, or maybe they even fill up areas, whatever that means. And they do so in a way that depends a lot on boundary conditions. Some of the structures that we have seen, they look like simple arcs or rays, and the number of such structures, they admit simple counting in terms of L. Usually the number of arcs and so on, they are linear functions in L. But the structure that pinches the real axis at ZC, let's look at it again. It's over here. That doesn't look like a simple curve. It looks more like some kind of wedge coming in with some thickness. Yet series studies favor the Ising universality class to an enormous precision right at ZC, and the Ising model was integrable. And to end, there's a fascinating condensation of features at this magical point that Paul Fentley and others have studied at Z equals -1. That is to say, if you look at Z equals -1, you see this is sort of the origin of all these arcs. And that can obviously be so because all the eigenvalues are equimodular at that point. But let's come back to that. So, some more questions. Is there a singularity at Z equals -1 in the thermodynamic limit? And is analytic continuation possible beyond the zero-free regions? The last question is very hard, so please, if you have some idea. Well, if you look at these figures here, obviously some regions here don't have zeros. Okay, so suppose that the free energy is given by some expression inside here. Is it possible, even in principle, to take an analytic continuation of such an expression out here? Or might it be that there's something like a natural boundary, that is to say that all these zeros here, they show the condensation.
The thing is
Right.
the
Yes.
natural boundary.
Yes.
Okay.
So you see that the fact that all these zeros, they condense on some curves that close up, that does not necessarily mean that there's a natural boundary.
Right.
For the hard hexagon model, I just told you that both expressions can be analytically continued to the whole complex plane.
You probably said it, but I forget. For hard squares, is ZD the end of the line segment as well as for hard?
Yes. So the values ZD, of course, are not identical for
No,
both
but
cases, but I called them ZD both of them.
yeah.
So let me go on. So let me talk a little bit about transfer matrices. So the partition function can be built by a linear operator acting on the particle positions within a row of the lattice. And that transfer matrix, that's a very well-known operator to most of this audience, presumably even to mathematicians. It's a well-known thing. So it takes it given. So it works on the space of configurations of particles within a row, and each configuration is associated to some kind of conditioned partition function, which is the partition function on the part of the lattice which is, say, below the row where I am, conditioned by the positions of the particles in the last row. And the transfer matrix T, it takes that information and it propagates it one lattice step upwards in such a way that the partition function, when I have periodic boundary conditions in the propagation direction, becomes the trace of T to the power LV, where LV is the height of my lattice.
So what's the law that makes the evolution?
Law that makes the
Yeah, that is to provide the correct Boltzmann factors that build up the partition function. So the Boltzmann factors, they are defined in a local way because you just need to provide a factor of Z for each particle that you put in. So if you have a certain number of particles in this row, and then you go one row up, well, then you see you need to sort of give a weight Z for each particle that's being swept over. If I want cylindrical or cyclic boundary conditions, or free boundary conditions, the expressions are a little bit different. As long as the boundary conditions are periodic in the evolution direction, I'm taking a trace, but I'm doing that of either the transfer matrix that sees periodic boundary conditions in the other direction or free boundary conditions in the other direction. And if I want free boundary conditions between the bottom and the top of the lattice, then I'm going to have my transfer matrix working in a sandwich way. It's sandwiched between two boundary vectors that provide the boundary conditions in the first row, and in the last row it provides the last bunch of factors of Z to the various configurations. And here the symbol TR means just an ordinary matrix trace. So if I express all of this in terms of eigenvalues and eigenvectors, then for the toroidal case, I'm just going to get the sum over eigenvalues to the LV's power. And same thing for cyclic, but with the other transfer matrix. Whereas for cylindrical and free boundary conditions, these eigenvalues, they are going to be multiplied by some multiplicities which are given by suitable products of these boundary condition vectors. I should also discuss a little bit symmetries. So the transfer matrix that sees periodic boundary conditions across, and also these boundary vectors here, they are invariant under translations and reflections. And that means that momentum and reflection parity are good quantum numbers. And so these amplitudes here, they vanish unless VCK lies in the sector with zero momentum and positive parity. The free transfer matrix is invariant under reflections for hard squares, but not for hard hexagons, because the hard hexagons, they lie on a triangular lattice. A triangular lattice, that's a square lattice with diagonals added, and those break the reflection symmetry.
Is it conceivable that you can apply the transfer idea of evolution
in three, cubical grid?
In 3 dimensions? Yes, one can do that. As long as, you just single out one direction,
Yeah.
and then you cut by planes. So that's a construction that works in any dimension. Of course, the reason why the transfer matrix is so popular in statistical mechanics is that it's very good for analytical purposes, and it has some good properties in 2 dimensions, because once you have cut your system, then things lie on a line. So there are strong constraints I mean, you can see the left and the right, and that's very important in almost all analytical techniques in 2 dimensions. That's why it's so difficult to solve anything precisely in 3 dimensions. That's because that breaks down. And even as a numerical tool in 3 dimensions, usually the number of vertices that you see in such a 2-dimensional plane is going to be so large, and the number of states is going to be so large that you cannot study reasonably large systems in this way. So here's one theorem, because I have to show at least one theorem. There will be a little bit more later on. Suppose that you have some function that I'll call Zn of z. That's a sum over some amplitude. Okay, I'll think of those as amplitudes times eigenvalues raised to the nth power. And let's suppose that the alpha and the lambda are analytic on some domain in the complex plane. Then these are like partition functions for a system of height n layers. Now consider the 0 sets, so the z in the domain where these partition functions are 0. And let's consider specifically S infinity, which is the set of their accumulation points in the limit when the system becomes large, when n goes to infinity. So you see what I'm talking about here. I'm really trying to describe the fact that these points here, there can be accumulation points of such zeros. So let me get back. Excuse me. And in terms of the eigenvalues of my transfer matrix, let's call a given index K dominant if the corresponding eigenvalue in norm is larger than or equal to all other eigenvalues. And suppose also a little technical thing. Then basically that eigenvalues are not trivially proportional with proportionality constant of unit norm. Then there's a theorem by Biraha, Kahan, Weiss, slightly improved by Sokol. A point belongs to this limiting curve, or this set of accumulation points, if and only if either there's a unique dominant eigenvalue at z, but its amplitude vanishes, or there exists more than one eigenvalue which is dominant, that is to say at least 2 are equimodular. So I won't go into the proof, but you can see that, if you just act like a physicist and forget about mathematical rigor, it's absolutely clear what's going on. How can an expression like that be 0? Well, to be 0, it has to be anomalously small, right? If I order the eigenvalues according to their norm, then I can make this exponentially small by putting the amplitude of the leading eigenvalue equal to 0. Or alternatively, I can have 2 eigenvalues which are equal in norm, and I can play on their relative phase so that the 2 of them completely cancel out from this expression here.
Sounds like a proof to me.
Yeah, well, if you have to be serious, you have to really prove it. Okay, so in case number 1, z is obviously an isolated point in S infinity because this alpha k here, it depends continuously on z. So if you move z a little bit away, then it won't be 0 anymore. Whereas in case number 2, there's going to be a curve in S infinity because you can play on this face and trace out a continuous curve.
Fixed or also depends on them?
And so in this case here, m is what was it? m is the dimension of the transfer matrix, so that's kept fixed.
Mm-hmm.
Okay, so to my great regret, case number 1 does not occur in these hard particles.
Do you know a case where it does?
Yes, so that's why I insert an intermezzo.
Oh, okay.
So there's a wonderful model that generalizes the Ising model, which is called the Potts model. Its partition function is now such that, well, spins now can take q different values, and I give a negative value to the energy when neighboring spins are aligned. So it works just like the Ising model, except that you have q different states. It's again defined on a grid. And using a little trick, you can rewrite the partition function in such a way that you sum over all subgraphs, subsets of edges A, and you give a weight exponential k minus 1 to each edge in that subset, and you give a weight q to each connected component in the subgraph that's generated by the same vertices and the subset of edges. So there's a 3-line proof of this expression here, but it's exactly the same as that. And it has the immense advantage that once I'm here, I can now completely forget that q was an integer in the beginning. Now I can treat it as a parameter that can take real values or complex values as you wish. And once I specialize it to the integers, I'm back to where I started. So that makes it easier to study the analytic properties of this set here. So that's the 14-Castelline representation. Now, if you take cyclic boundary conditions, then you have to take care, right? Because there are now free boundary conditions across, and there are periodic boundary conditions in the propagation direction. So before, we did that by a trace of the transfer matrix to some power. But if you have to count those connected components, you see that that trace is not an ordinary trace. It's something that's called a Markov trace. And it's possible to decompose combinatorially or by other means the Markov trace on standard matrix traces. But when you do that, you're going to pick up some eigenvalue amplitudes. So U, that's the Chebyshev polynomial of the second kind. And little l here turns out to be the number of connected components that turn around the periodic direction. So if you have several connected components that wrap the periodic direction, well, that's L, and then you get this expression here. And the Chebyshev polynomials, they can vanish at certain values of Q. And the places where they vanish, that's very much related to what statistical physicists call minimal models. And it has deep links to representation theories of quantum groups. So to see this as at work, let's take the Q-state Potts model, where I put this parameter v equals to -1 so that it becomes a coloring problem. So I'm considering colorings of the square lattice and the triangular lattice such that neighboring vertices have different colors. So that's a polynomial in Q. So I can analytically continue it to the complex plane. And the red guys here, those are the partition function zeros for a large system of size 6 times 60 or 6 times 60 also on the other side. The black curves are those S infinity limiting curves that you see cut the plane into different pieces. And sometimes in between here, there are isolated limiting points, and they come from this Chebyshev polynomial here. And they sit at values of Q such that Q is equal to 4 cosine squared of pi divided by an integer.
Famous Baraha numbers.
The so-called Baraha numbers. Well,
Sammy Baraha
Baraha numbers.
from Queens College.
Yes.
Die conjecture.
Huh?
Die conjecture.
So I should mention that this formula here can sort of be derived by quantum group considerations. It was done by Saleur, then it was found in another way by Zhang and Strug. It was proved in a combinatorial way by Richard and myself. If you now move to toroidal boundary conditions, well, you won't be disappointed, because what happens now is that you're going again to have this decomposition according to how many connected components wrap around the periodic direction. But then there's also the other periodic direction, which means that the connected components, they can also spiral along, so they have some momentum. And so if M is divides L, then I'm going to get this expression where alpha depends both on L and M.
These regions are different colors or spins pointing up and down, the ones?
Yeah, so those are they come from this this expression here, where I have these subgraphs here of regions where the spin take the same value, and if there are L different connected components that wind around the time-like direction, then I'm looking at the Lth term here. Okay, but since now these connected components can also spiral around the other periodic direction, then there's going to be some momentum. And the amplitudes are now going to be given by this expression here in terms of some certain lambda. And lambda contains all kinds of funny things. Now you see the Chebyshev polynomials of the first type. And you see mu is the Möbius function, and phi is Euler's Tothian function. So that was a really hard thing to prove. There was some kind of field theoretical argument given by Reed and Saleur, and then with Richard we provided a combinatorial proof of it. And if you look again at the coloring problems on a 7 times infinity torus on the square triangular lattice, you can see now that the zeros do not sit at all the Biraha numbers anymore. They actually, you see the one sitting at the golden number here, 4 cosine squared of pi over 5 is no longer there. You can even do it for graphs in dimension larger than 2. So usually in statistical physics, we think that we should give in if the dimension is larger than 2, but...
How do you formulate the dimension of a graph?
Okay, so... let's just say a non-planar graph, okay? So it's possible to have a non-planar graph which is so regular that I can consider it as some kind of strip, but now where connections can sort of jump over one another. And I take again periodic boundary conditions in the time-like direction, then things can be decomposed both according to the number of wrapping clusters and a representation of the symmetric group living on them, and then the eigenvalue is now going to be something like, well, precisely this, where the lambda are the row length of the Young diagram. So you see, this is interesting because it means that even if you cannot solve a system in dimension, well, you cannot solve statistical physics problems in dimension higher than 2 usually. Nevertheless, it's sometimes possible to completely control certain representation theoretical aspects of them, and, for example, give this exact expression for the eigenvalue amplitudes. End of the intermezzo. I'll just show, to finish, I'll show the zeros and the equimodular curves on a certain class of non-planar graphs, which are called generalized Peterson graphs. And it looks like that, and you can see that now it's the integers that can support isolated limiting points, and there is no 4-color theorem, so things can go out beyond 4. Okay, so let's get back to the limiting curves. So if I have 2 eigenvalues which are equimodular, it means that the ratio of lambda 1 and lambda 2 is some phase factor. And when LV is large, then the partition function will be 0 close to the point where exponential minus theta LV is equal to -1, obviously. So if I define little s as the arc length along this equimodular curve and the density of zeros in this way, then you see that the density of zeros is going to be related to a derivative of this angle as I move along the arc. And we saw that vividly on some of the previous figures, that sometimes on these curves the zeros are very dense, sometimes they are less dense, and that just tells you something about how fast does this angle move when we go around this limiting curve. Let me now show you what these limiting curves look like for hard squares. So here you have all four boundary conditions on one single graph: toroidal, cylindrical, cyclic, and free. And the transfer matrix, they have been correctly constrained to the zero momentum and positive parity sectors when needed. I superimpose on these things here, which are for a system of width 16 of infinite aspect ratio, of course, now because it's a transfer matrix. I superimpose the zeros for an L by L lattice. Okay, so this is comparing then zeros for aspect ratio 1 with their accumulation points for aspect ratio infinity. You see sometimes these zeros, they actually fall right on top of the curves, or almost. And sometimes there are some quite vivid differences. And so I get the curves now by diagonalizing the corresponding transfer matrix. And then I explicitly find the place where they are equimodular. So those are very, very serious computations. It takes a long time to do so. Well,
65,000 dimensional matrix to diagonalize.
Oh,
that's not so much. Oh, well, I could lecture for an hour about how you do that.
But you don't have an app.
There's only several million, but several million, right?
Well, you use
2 to the 16.
You use hashing, you use sparse matrix factorization, and you use Krylov subspace techniques for diagonalizing. And then you think a little bit about what you're doing. Okay, so why is it that the difference between aspect ratio 1 and aspect ratio infinity sometimes seems to be almost absent, and sometimes it's vividly pronounced? Is there any way to relate the two in any obvious way? I don't have any precise answers to that. Why are these guys here so complicated? Why is it that the number of curves going out of this point here is something that relates in a simple way to L? If you count these guys here, you will see that maybe there's about 16 of them. And here the number of bubbles here is also simply related to the number of sides in your lattice. That's all interesting questions. Here's the same thing for hard hexagons. This one here, that's more or less the thing that we liked to see, I guess, because it looks very much like the partition function zeros that we had before. And this black curve here, it's very, very similar to the thing that was obtained by equating Baxter's two expressions in norm. But still you see that there is this necklace region here. And on the other figures, there are these strange branches going out to infinity. This is not so mysterious as it might seem, because it has just to do with the fact that asymptotically, for very large density, there are degenerate eigenvalues sitting in different momentum sectors. So as you go along here, the momentum will change. And you see that along those branches, there's actually no partition function zeros. It looks like the density goes to 0. So that's another interesting question. Why is it that sometimes along these equimodular or limiting curves here that there is almost no zeros, and sometimes there is plenty of zeros. How can I determine, once I have taken the pain to compute these equimodular curves, which part of them are relevant for the problem and which parts are seemingly almost irrelevant?
But there's this open doorway on the right that wasn't in the earlier pictures.
Well, that's going to close when 21 goes to infinity.
Oh, okay.
21, that's just when the computer gave in. So that I already said. And that I also said. So I can go on. Yes?
Does Wilson renormalization can be fit into this to have more grid points by renormalizing Wilson renormalization, do numerical experiments? I mean,
well, let's see. So I mean, up till these computations are just exact computations on the given transfer matrix. So it's quite possible that there is some approximate technique of doing some kind of renormalization that I don't know.
okay.
I have to ask Barry for a long time. Am I supposed to talk? Because
Let me make a comment. The banquet is at 6 o'clock upstairs, and it was commented that 6 o'clock is a very awkward time. It's not time enough for people to go back to the hotel and come back, but it's also awkward in that people just have to hang around here. So you are able to have more time because people are trapped here if they're going to go to the banquet.
Okay, thanks. Okay. So there was this ZD. ZD, that was the rightmost endpoint of this little segment on the negative real axis. So here again you see a very vivid difference between hard hexagons and hard squares. Because for hard hexagons we find that there is an unbroken line segment in this equimodular curve. So the thing that looks like a line segment, it is one connected piece. And the discriminant of the characteristic polynomial of the transfer matrix has only double roots where the equimodular lambda are real and equal. And the same is found for the other transfer matrix. However, for hard squares, this seemingly connected line segment is not at all connected. There are small gaps. So more precisely, so there exist segments of the interval between -1 and ZD where the dominant eigenvalue for both TC and TF is real and non-degenerate. And that leads to small gaps that are so small that you cannot really see them, but here I have listed some of them for various kinds of sizes in the transverse direction. You see the two endpoints here, and you see the gap, and you see the sign of the eigenvalue within the gap. And you see, as the system size grows, the size of, so these gaps become more numerous, and they become very small. So when the size goes to infinity, the gaps in TC and TF, they approach each other. The number of gaps increases linearly, and they smoothly start filling out the entire segment. So it means that it becomes some kind of Swiss cheese, some kind of Cantor set or something. And the width of the gaps decrease presumably exponentially, I mean, at least according to these computations, as the gap location moves to the right. And all gap sizes decrease presumably also exponentially when the size goes to infinity. So here's a conjecture. It's nice to conjecture something because then you can be proven wrong. When the size goes to infinity, I conjecture that the gaps form a dense set of measure 0. So these gaps...
I don't understand the meaning of that.
So, well, I mean, so the gaps become...
The gaps tends to 0?
Yes.
Okay.
Yes. So those gaps, they lead to irregularities in the density of zeros. So we have computed the density of zeros for large systems, L by L systems. And if you just plot that density, it looks reasonably smooth. But if you start taking derivatives of it, you start seeing that funny things happen. There are some little glitches here. And that happens exactly when there's a gap and the eigenvalue phase is 0 or pi, and the dotted arrows are at phase plus minus pi over 2. And that does not at all happen for hard hexagons. So I'm getting close to the end. I spoke about hard hexagons and hard squares for such a long time. Let's get back to the Ising model. So recall that I have these parameters, u for 2 units of domain wall and x for a downturned spin. Here are the equimodular curves of eigenvalues in basically in the square root of u plane, or 1 over square root of u plane, with certain boundary conditions which are nice, or known to be nice for the Ising model, which are called Braskamp-Kunz boundary conditions. And you see on the left, you see the figure for zero field, zero magnetic field. And on the right, you see it with a very small field corresponding to x equals to 0.99. On the left, close to this point where, so this is for a system of width 8, okay, so this is supposed to pinch the real axis at the ferromagnetic phase transition in the Ising model if L had been sufficiently large. But there are all these branches here in the zero field case that go over to the imaginary axis. And as soon as you put in on just a very, very tiny field, then they instantaneously retract. That's interesting. How do they do that? At what speed do they retract? When you see the other guys here, which are close to the other point where the curve will pinch at the antiferromagnetic transition, you see they continue to go out. In the case where there is a non-zero field, the number of eigenvalues which are equimodular is equal to 2, 3, or 4, depending on whether you have singlet or doublet crossings. That's easy to explain from momentum degeneracy considerations. In the case of zero field, the eigenvalues are macroscopically degenerate. There's a color code on this figure here showing that sometimes there is up to 64 eigenvalues which are equimodular. Such things, such massive degeneracies, mean instantaneously that the conditions for the Biraha-Kahn-Weiss theorem break down, and also the relation between the density of zeros and the angle. That requires explanations. Finally, let me comment on the possibility of having natural boundaries in these systems here. Let me show you really a toy example where a natural boundary can occur. Let's consider two functions, two power series, sum of z to the n and sum of z to the 2 to the n. Both of those, by elementary considerations, they have radius of convergence 1. However, the first one, of course, can be easily resummed. It's equal to 1 over 1 minus z. It only has a pole in z equals to 1, and it can be continued to all of the complex plane except this point. Whereas the other function here, which was first considered by Kronecker, I believe, it has a natural boundary at z equals to 1. It means that there are singularities all around through which the function cannot be analytically continued. The proof of that statement is dead easy. Just look at the Math World web page. But I won't show it. Suppose now that I kind of play that f and g are like partition functions, and I will cut off the sum at some finite number of terms, and I will plot the zeros of these functions. Then without surprise, if I I mean, I told you that this was elementary. So if I sum this up to some capital M, of course, all the zeros are going to sit on precisely on the unit circle. They are going to be spaced with the same spacing. If I do it for the other function, you see that they almost sit on the unit circle, but there is some fuzziness to it, and the spacing is not regular anymore. Well, that kind of vividly resembles many of the things that we saw for hard squares. Okay, so one might dream that that might be some kind of a signature of an emergent natural boundary, but obviously that might also just be a red herring. I can't resist to show you a nice theorem that I found. Suppose that you have a power series with radius of convergence 1, and suppose that the coefficients take value in a finite set. Then Sigger has proved that either z equals to 1 is a natural boundary, or this sequence of coefficients is eventually periodic, so periodic for a sufficiently large n, in which case f is just a rational function with poles on the unit circle. So that theorem, that's like a way too big machine to show that this function here indeed has a natural boundary. So
coefficient 1, say 0 and 1, or minus 1 and 1 randomly, so no periodicity, this will always have a natural boundary.
this is an amazing theorem. I have heard during this conference several people use Sigger's theorem, but that was another theorem. So he has more than one theorem, and this one is a little known theorem. I believe it's called Sigger's gap theorem or something, and I find it very nice. So if Baxter's description of hard hexagons in terms of two expressions is complete, then hard hexagons cannot have a natural boundary. However, we found experimental math evidence that the description is incomplete, but that does not necessarily imply the existence of a natural boundary, of course. For hard squares, it might be that ZD is no longer an isolated algebraic singularity, just like it happens for the natural boundary of the Ising susceptibility. And just to wildly speculate, one may ask if any of the following unusual features are relevant for natural boundary questions. The fact that for hard squares I have 0 seeming to fill in areas, the fact that for hard hexagons I have this necklace region, and also the fact that there's a massive destruction, or destruction of massive degeneracy of eigenvalues for the Ising model as soon as I turn on a magnetic field. So here is a little movie that I want to show you just before we end. No. I'm trying to move full screen here. I'll manage to do so. Enter full screen. Okay, what is this?
What are you bearing?
You're very.
No, I haven't told anything. I'm recalling what this is. Okay. So in the beginning, you see two circles like that. In the beginning of the animation.
It's over, yeah.
So it starts here. Okay, two circles. What I'm showing here.
Fisher circle.
Okay, so what I'm showing here are the zeros of an Ising model in zero magnetic field in the U plane with Braskamp-Kunz boundary conditions. And then I'm taking this variable exponential minus 2h, and I'm turning it around the unit circle. so that the magnetic field goes from 0 to I pi over 2, which is known to be another integrable case, thanks to Berry-McCoy, on which the zeros can be proven to lie on a circle and a straight segment. And here you see how the zeros move around. So many of them, they move into 1 and minus 1. And when they do so, they have a very, very interesting dynamics. You see, they look like small elastic rubber balls that collide with each other. And when they are close, they move very fast. So that's when the magnetic field varies in that direction, it varies between two integrable models. But in between, it's not integrable. So, oh, I shouldn't have done that. Oops. Here's the same thing again. But here, so this is one circle and the other circle. And the little spaghettis that are jumping around, they show the complete trajectory of the ith zero when the magnetic field takes 1/2 turn around the unit circle. So you see that some of the zeros over here, they take a relatively smooth trajectory when they move from this set of two circles until this circle plus the axis. But you also see that some of the others, they have a completely insane dynamics. They have an almost chaotic trajectory that is fascinating. That comes from non-integrability. So, end of the movie, and soon end of the talk. So here are a few conclusions. Even for integrable cases, some work will remain. For example, how do we explain this necklace region for hard hexagons? How do we explain those branches on the equimodular curves for the zero field Ising model? Second point, non-integrable cases have interesting and largely unexplained features. There's a dramatic dependence on boundary conditions. There are gaps in the equimodular curves leading to irregularities in the density of zeros. The zeros sometimes lie on curves, sometimes they fill up areas. And when I change the magnetic field through a non-integrable region, there is going to be some kind of almost chaotic dynamics of the Ising zeros. And the third message is that even if I don't have integrability, it doesn't mean that nothing can be computed analytically or mathematically. So for example, for hard squares with fugacity -1, there's this massive eigenvalue degeneracy due to the existence of supersymmetry. And as I showed you for the Potts model, the degeneracies of eigenvalues, they can be figured out from representation theory, even for non-planar graphs, using cellular algebras, Temperley-Leap, Jones-Temperley-Leap, and the partition algebra. So I'm just 20 minutes over time, so I thank you a lot for your extended patience.
Since we're all just hanging out until the banquet, and it's overtime, let's not have any more formal questions, but people can come up and ask Jesper. And I'm told by the people upstairs that if you haven't still signed up for the banquet, that you're welcome, that there's still places for people who haven't signed up.